All right, welcome. It's Thursday. We are going to do um, today Riemann sum from a table. And for a warm-up, I wanted you to try this problem. This is a old AP problem, just simply taking the derivative. So I'd like you to pause the video and take the derivative, and when you're done, give yourself about 3 minutes for this, and have somebody come up and work the problem at the board, and when I get back, we'll see if you guys could get the right answer. So you can go ahead and work in groups, but pause the video, and then we'll continue in about 3 minutes. Okay, one of the things that we've been talking about is Riemann sums, and it's not the one is that the one I want? One of AP's favorite tricks or things to do is to give you all a Riemann sum from a table. And this is an example of an old AP problem, or at least broken into parts, that you had to evaluate a Riemann sum from a table. So the area under curve is a car is traveling so that its speed is never decreasing. So it's always going up during a 12-second interval. The speed at various moments is listed in the table below. Sketch a possible graph for this function. So this is just plotting points. It doesn't have to be very accurate. We're just kind of seeing. So 0 was 30. We're going from 30 to about 70, 40, 50, 60, 70. We'll go by tens. And we're going intervals of 3, 6, 9, 12. Okay, so 0 is 30, 3 is 37. This is just an estimate. 6 is 45, so 30, 45. 9 is 54, 54. And 12 is 65, so that's up there. All right, so there's my curve, sketch a possible graph. Okay, I don't really know. It just looks something like that. All right. Estimate the distance the car traveled during 12 seconds by finding the areas of four rectangles drawn at the heights of the left input. So we're going to do a left Riemann sum, and this is called left Riemann sum. So we're going to use the left-hand side. So what we're going to do first to figure out the width of the rectangles, I think it's kind of obvious what it is, but what you do to find the width of the rectangle, so they call that delta x, it's the limit b minus a over the number of rectangles. So we're going from 0 to 12 seconds, so b would be 12 and a would be 0. We're going to divide that by 4. So obviously they're each 3 long, just like what they told us. I'm going to draw some vertical lines going up at intervals of 3. And I want to do a left-hand sum. So a left-hand sum means that I'm picking the left-hand side of these lines for the area of the rectangle, so the height. So right here, that's a lefty. And we're going to go where it hits the line, draw one going over. So I'm drawing this in green. All right, so those would be my heights of my rectangles. Let's see. So estimate the distance. So the distance traveled is basically the area under this curve. And so what I'm going to do is find the area of all the rectangles and add them up. So the width of the first rectangle is 3. The height would be f of 0, which is 30. The second rectangle has a width from 3 to 6, has a width of 3. And the height is f of 3. So it would be 37. The next rectangle from 6 to 9, again, a width of 3. And the height, picking the left-hand side, would be f of 6. So that would be 45. And the last rectangle between 9 and 12 has a width of 3. And its height would be f of 9, which is 54. And I could add that up into my calculator, and that will give me an estimate of how far the car traveled. I would do that on a calculator. On an AP test, I could leave the numbers just like they are, and I wouldn't have to solve that unless they specifically asked me to. So probably I would leave it that way just so I don't make any mistakes because then I don't get the credit. All right, so I get 498. What are my units? Let's see. Speed, feet per second. So we're talking feet. All right. So that's an estimate of how far it traveled in 12 seconds. And now what we're going to do for the second part, here in part C, they want me to use right endpoints. So take a second, pause the video here. I'm going to need to erase the green part there because we're going to do right rectangles now. So I'm going to erase this. All right, so for right rectangles, I'm going to draw that in blue. All right, now the only difference is the height of the rectangles is now going to be the right-hand side. So we're going to start here where it hits the curve and go over. So the ones in blue would be my right-hand estimate. Oops, that's over a little bit. All right, and then this comes up and it's there. All right, so the blue rectangles are my right rectangles. So rather than starting at 0, I'm going to start right here at 3. So my width of my rectangles is still 3, but now the height here would be f of 3. So I would start this sum here. So f of 3 is 37. The next rectangle from 3 to 6, they still have a width of 3, but my height is now going to be here. So it would be 45. And then the next rectangle from 6 to 9 would have this height 9 would be 54. And the last rectangle would have a height of 65. And you can plug that in a calculator and get an answer. So the thing is, with the left, I'm going to start at 0 over here. And with the right, I'm going to start 1 in. I'm going to start at 3. So with the left, I'd go from 0 to 9. With the right, I'd go from 3 to 12. Okay. So, and I'm just going to plug that in my calculator. And I get 603 feet. Okay, so you can go left or right, and it doesn't really matter. But the table are a favorite AP type of question, which brings up something. There's no requirement that the rectangles have equal width. All right, this is important because there are times in an AP test they'll just give you a table and say use this many rectangles, and you do what it says, but they don't have to be equal width rectangles. They usually are, but there's no requirement. So we'll look at an example where they did that to them. All right, so this example is an old AP problem. It says water is flowing into a tank over a 12-hour period. The rate at which the water is flowing into the tank at various times is measured, and the results are given in the table below, where R of T is measured in gallons per hour, and T is measured in hours. Tank contains 150 gallons of water. Now this is important because when you integrate or when you find the area under a curve, you find the net change. So if I estimate the integral of this, what I'm really doing is determining how many gallons went into the tank between 0 and 12 hours. So what I have to add what I started with, which was 150. All right. So it says estimate the number of gallons in the water in the tank at the end of 12 hours. By using a left Riemann sum, so I'm going to start at 0 here, that's the left-hand side, with 3 subintervals. All right, that means 3 rectangles, and values from the table. Show the computations that lead to your answer. So when I look at this, I don't have a lot of choice. I can go from 0 to 5, that would be 1 rectangle. 5 to 8 would be your second rectangle, and 8 to 12 would be your third. So they're not equal width, and that's fine. Okay, no problem. So from 0 to 5, the width of that rectangle would be 5. And I'm using a left Riemann sum, so my height of that particular rectangle is going to start on the left, so it's going to be 8. For the next rectangle, we're going to go from 5 to 8, so the width of that rectangle is 3. And using a left-hand sum, the height would be 8.8. And finally, for my last rectangle between 8 and 12, that's 8, 9, 10, 11, 12, that's 4, width of 4, and the height height, picking the left-hand side, is 9.3. All right, and again, I'm going to plug this in my calculator. And I get 103.6 gallons. Now, what this represents is the net change, is how many gallons went into the tank between 0 and 12 hours. And the question they're asking is what do they want? The number of gallons in the tank at the end of 12 hours. So I have to add to this what I started with. So I simply add 150 gallons to it. And I get 253.6 gallons in the tank, that's all. Okay? So this is an old AP problem. It threw a lot of people off because of the unequal widths. The rectangles do not have to have equal width. They just have to have the right number of subintervals, which was 3. All right, so then in part B, it says estimate the number of gallons of water in the tank at the end of 12 hours by using a right Riemann sum with 3 subintervals and values from the table. So pretty much all I'm going to do, I have the same widths, but now I'm going to do it from the right-hand side. So I'm going to start here. I'm going to use these 3 heights right here. So the first rectangle has a width of 5 and a height of 8.8. Okay, the second rectangle has a width of 3. 5 to 8 is 3. And a height, we're going to pick the right-hand side, so it would be 9.3. And the last rectangle has a width from 8 to 12 is 4, and the height would be 9.2. All right, again, I can plug that in my calculator. And I get 108.7 gallons. Now that is not what's in the tank, that's how an estimate of how much it went up. So I'm going to add to this again what I started with. So I get 258.7 gallons. Okay. So this is actually an old AP problem that popped up a few years back that I recall. It's part of one. There's other parts to it, but that was definitely part of it. If you need to catch up, you can pause the video. Otherwise, I'm going to go on. All right, so to estimate the area bounded by the graph of f of x and the x-axis between the vertical lines x equals a and x equals b, what we do with the Riemann sum is partition the area and divide it into subintervals. Yesterday we drew rectangles with the height at the left endpoint or the right endpoint, midpoint 2. Today we're going to draw rectangles at some general point within the subinterval, not necessarily at the left or right endpoint or whatever. I mean, the height of the rectangle can be anywhere you want where it hits the curve. So what they're trying to tell you is, you know, if I split this into whatever n rectangles, I can make these rectangles anywhere I want. I could do it at the left, I could do it at the right, I could do it at the mid, I could also do it like halfway up. All right, it doesn't matter. But they're going to call this general point x sub I because we have I. I'm going to say we have I rectangles, and you know, this is f of x sub I here will be your height of your rectangle. All right, so your height of your rectangle is called f of xi, where I is some point in the interval. All right, we're going to write a Riemann sum as well. All right, so let x equal ck be any point in the kth interval. Okay, so draw a rectangle with a height f of ck. So sorry, rather than using xi, they're calling this ck. All right, so this is the point ck, and this is f of this point ck. Okay, so you got some height and some width, or some width and some height. You're going to just multiply those together to get the area. So the area of the rectangle, the height would be f of ck, and the width would be what we call delta x, all right? Where delta x would be the distance between 2 points that I'm comparing, all right? It does not have to be the same, so we'll call it delta xi or delta xk, I guess, because that's what they're using. So these are all delta x's, they're the width of the rectangle. And of course, as dx gets smaller and smaller, it goes to 0 and the area gets more accurate. So So the sum of all the rectangles, basically the way that they write it is just we do a little Riemann sum here, the sigma. We're going to sum over k somehow. We're going to have, let k go from 0 to n of f of these ck's times your delta x's. So k, I guess. It's f of x, yeah. So the sum is called, this particular type of sum is called a Riemann sum. Named after Riemann, mathematician. It's not really all that critical just as much as you understand that I'm summing up areas of rectangles. The smaller and the more frequent the rectangles get, the better the estimate of the area. This is what they refer to as a Riemann sum. So to get the exact area under the curve, what I can do is take my sum here, and if I have an infinite number of rectangles, or as delta x goes to 0, I'm going to exactly recover the area under the curve. So all they do is add a limit here. I'm going to write it the way it was written there. It's the limit as the number of rectangles go to infinity, or delta x goes to 0, of f of the sum. We're summing this over, what are they doing, k. Equals 1 to n. It could be 0 and n. It doesn't matter. F of ck times your delta x k. Okay? So to talk about exactly recovering the area, what we're saying is let the rectangles get, the width get smaller and smaller and smaller, and eventually you'll have an exact representation. This is what we refer to as an integral. So here you see this sign here, pretty sign, integral from a to b, f of x dx represents the assigned area under a curve. We'll talk about that in a minute. So f of x is your function, dx is your delta x, but I'm letting delta x go to 0, and they replace it with a dx. So this and the Riemann sum are equivalent. All right. I don't know why I wrote that twice. Don't know. Okay. But anyways, that's saying the same thing. All right, so this is what's referred to as a Riemann sum. The signed area under a curve would then is represented by this integral sign. The limits a and b represent the area underneath the curve. So basically, if I have a function and I want to find the area under this curve, instead of splitting it up into rectangles, I do an integral. That's where I have rectangles of 0 width. I go from a to b, and when I do that integral, I get the signed area under the curve. And what I mean by signed area is the area above the x-axis is positive. If I have a curve and I want this area here, the area underneath is negative. All right, so that's why it's called the signed area. This particular thing is called an antiderivative. It is the opposite of a derivative. It's an antiderivative. It's an integral. Integrals and antiderivatives are the same thing. So to write a Riemann sum, okay, what you're going to do is kind of undo your integral. So you figure out your f of x clearly is x squared, and I'm integrating from 0 to 2. So the first thing I have to do is find the width of each rectangle. So the width is the delta x. And delta x, as you recall, is b minus a over the number of rectangles. So in this case, a is 0 and b is 2. So it would be 2 minus 0 over n. All right? And we're using 4 rectangles, so in this case, my n is 4. So it would be 2 over n, which is 4. So it's 1/2. So my delta x would be 1/2. All right, find the height of each rectangle. So the height would be f of x, right? So the height is just the f of x. So the height would be f of x, okay? And what you basically do is you're going to sum this. Now your x is going to change. What you do is, I'm going to call this xk or whatever, xc, whatever it was. You're going to sum those up, okay? And so what you're going to do is your delta x, you're going to start. The problem is, am I doing a left or a sum or right? It doesn't say. So if I start at 0, what what you're going to do is you're going to find, so xk would be a plus I times delta x. A is where you start. So in this particular case, it would be 0 plus my summation. I'm sorry, make that a k. Make it a k. So it's k times delta x would be 1/2. So I get k over 2. So what I'm going to do is take my x, my f of x squared, and I'm going to replace the x, right, f of x equals x squared. I'm going to replace the x with k over 2. So it would be k over 2 squared. All right. And my last step is to write it as a sum. So what I'm going to do is do my sigma, because it's f, basically as a Riemann sum, it's f of xk times delta x, and I'm going to sum this thing. All right, so I can do a left or right, and they didn't specify, so I have my choice, so I'll do left. So I'll let I go from 0 to 3. You see that gives me 4 rectangles, 0, 1, 2, 3, or from 1 to 4, they didn't specify. F of xk is this. Make that k, I'm sorry. So it'd be k over 2 squared times delta x, which we decided was 1/2. And that would be the Riemann sum. Oh, one more thing. We're going for rectangles. So that would be the Riemann sum to represent that rectangle. And we'll talk more about this. Don't freak out about that too much right now. All right, so that's today. See you sort of tomorrow. Okay, we'll talk more about Riemann sums tomorrow. I just wanted to introduce that today. The main thing is you should be able to get a Riemann sum from a table.